this little bit of topic. And today we will hear this, where we apply the technology for this development of this knowledge of the physics. So today we have two lectures on that. Our first lectures will be Professor Elisabetta Barberio. She is the director of this Center of Excellence for Dark Matter Particle Physics, and also Thomas Levy, Professor of Physics, University of Melbourne. Actually, her main interest topics is this dark matter and cosmology. And she is this PI, or you can say that first person in Australia to start many of these activity in Australia. And so you may understand why we choose her to give these lectures. And of course, her group is also involved in the Atlas experiment. So without much more introduction, I request Professor Barberio to start.
Thank you very much for the invitation to give this lecture on dark matter. There will be two parts in this lecture. The first part, I will give you a little bit of an idea what the kind of signal we're trying to do. And in the next lecture, a little bit more like what it entails to build this kind of experiment. And it's a kind of adventure. They're very different from collider experiment. So first of all, I start with, this is not the usual pie chart you may see. This is more the pie chart in which we speak about the mass budget of the universe, in which I would say that 20% of the ordinary matter, all the matter we see in the universe, star, galaxy. And when I call ordinary matter, I've been a little bit generous because I put also neutrino in. So it's not only baryonic matter, there is also neutrino in. They represent only 20% of the matter of the universe. When you see a galaxy and a cluster of galaxy, we know that there is much more matter that we can see. And this much more matter that we can see, this with so-called dark matter that is unknown composition, you represent 80% of the matter of the universe. So it's the majority of the material in the universe there. When we speak also about the energy density of the universe, we find ourselves that ordinary matter plus neutrino is about 5% of the energy density budget. And the majority of the universe is dark energy, but we are not touching dark energy. This is a much more complex problem. So why do we know dark matter? We know dark matter because gravity tells us that there is dark matter. This is is an example of gravitational lenses. In the sense when light travels to the space, bend as the space bend because there is gravity, and produce kind of images like here there are three galaxies. So the same galaxy here, three galaxies, and you can see the galaxy, but then also you see the mirror, how the galaxy look like after they pass gravitational lenses. This is a true one. This is not made up. It's coming from the Hubble telescope. And this is a classical example of how the bending of light around a known mass, because you don't see any light from it, is an example that you have dark matter.
Conventional one, if you
thanks. Yes. So now we go to our Milky Way. As I say, dark matter represents 80% of the matter in our universe. And so when we look at our Milky Way, this is, I think is Andromeda, that it looks like very similar to our Milky Way. So you can see what we see with telescope, or which kind of telescope, doesn't matter the wavelength, is a spiral galaxy, quite flat as a disk with a bulge in the middle. But then when we look at all the other parts, like macro lenses, velocity of the star in the galaxy, and many other measurements, we realize that our galaxy is surrounded in a big spherical halo of dark matter. So if we look at the matter in our galaxy, we see that this diffuse halo over here is all our galaxy, which this is the baryonic matter plus neutrino, and these represent dark matter. And so the difficulty or the challenge in this kind of experiment is what is dark matter and how we see something that we know interact gravitationally, but for what we know up to now, we have absolutely no idea how interact with baryonic matter, with our matter, and how to detect. And here is the challenge, because if we put together everything we know from astrophysics and cosmology in dark matter, and that could be another lecture or 3 lecture or 10 lecture there. He boiled down that the only thing we know that dark matter interacts gravitationally, and then it can interact or non-interact with normal matter, and the mass of this particle can go from very, very tiny, much tinier than a neutrino mass, to very, very large, to the point that can be much larger than the energy of the LHC. And there are also, even if it's getting excluded more and more, people that think that dark matter is nothing else than black hole or similar to black hole, and can be particle or object that are 30 times the solar mass. This represents a big challenge for the field, because you're looking something that the mass can span over many, many orders of magnitude, and the interaction with normal matter can change depending on the mass and the hypothesis. So you can see here, in this arrow over here, all the kind of hypotheses we can have on dark matter. Here, for example, we have what we call a hidden sector dark matter. We have this dark matter particle that has some property, and the way they interact with normal matter is something that can be described, but we don't know exactly what it is. There are many, the classical WIMP that is getting a little bit more sparse asymmetric dark matter, in which we also have a particular model for many, many different parts, and all of that. And then if the dark matter particle is very, very tiny, well, then we enter in a new kind of idea that we can have what we call an axion. An axion was predicted in the standard model to solve the strong CP problem, but is a kind of particle that has, differently from the dark matter hypothesis here, the dark matter may interact with an electric or a magnetic field. And in the next lecture, I will give you an idea how to build experiment in this kind. And you can see here the current experiment, just few of them, and future experiment. And here we're speaking about really many, many different experiments in many, many different countries. So differently from collider experiment, where experimentalists sit together in the same lab, because like the LHC experiment here, different countries, they have their own experiment. Some are very large, some are very small, and the technology can go, because for dark matter particle above the GV or GV or above, we can see the dark matter using nuclear recoil when the dark matter has an elastic interaction with the nucleus. Here we can have a dark matter small enough that can have interaction with the electron, and the nucleus is not affected. And then we enter in this part here, absorption, where we can see is we are looking now at different technology from the classical particle physics technology you do. We look at bolometer, we look at measuring heat, the heat released by dark matter in a material or others. And then when we enter in the axion, well, you're measuring change in electromagnetic fields. In practice, you have a kind of radio. You produce a radio, and we will see in the next lecture to see dark matter. So today I will concentrate on WIMP, so weakly interacting particle, and this has been a lot of effort. Most probably is where most of the effort has been done, because there are many different motivations from the theoretical point of view to have WIMP. I will leave to maybe to another lecture that. Just believe me, this is why people thinking that maybe is the most probable candidate for now. So what happened? Well, dark matter can interact with standard model of baryonic matter in our universe, and there are different ways you can see. You can see because you smash proton and you produce dark matter. This is what, for example, the LHC can see. You can have dark matter interacting in star galaxy or in astronomical object and produce light. And so that's what we call indirect detection. And there is a lot of hunting going down there. And then what I'm concentrating there is putting detector, sometimes underground, somewhere underground, and we'll explain there on Earth, and then trying to see that dark matter will interact with this detector. And that's what we call direct detection. So direct detection is what I'm concentrating today. So How direct detection? I will concentrate and give an idea. We start with how the fields start. You put an experiment underground here, if there will be ever an experiment in South America. And then you have the dark matter interact with the nucleus and produce a nuclear recoil. This interaction is assumed to be elastic. And dark matter, in first approximation, is assumed to be spinless, spin zero, so also there. And so what we need to do is building an experiment that can see the energy released in this interaction. So the nuclear recoil will produce, the nuclear will recoil, there is a kinetic energy, and we can see this kinetic energy in different ways depending on the technique. That goes from the heat released in the interaction, scintillation because we have particular material, or just looking at particle moving in gas chamber or liquid gas chamber, in which we see trail of ionization. So what is the expected rate? So what I need to look when I have my interaction is a collider, the collision of my WIMP with my nucleus. As I said, I assume that is a scalar, my WIMP. I also assume that the collision is elastic. If it's inelastic, I need to change. So my rate of interaction depends on different part, depends on the mass of my particle, of my dark matter particle, on the cross-section of dark matter particle with my target, with the material of my target, and this is where the particle physics is all the theoretical assumption of the interaction of dark matter with normal matter enters. And then it depends on how much dark matter I have in my galaxy. So, and this is described by the density of dark matter locally where the Earth is, while Earth goes around the sun and around the center of the galaxy. The velocity, the relative velocity of dark matter with respect to Earth. Dark matter is called dark matter when we speak about WIMP, means it's a non-relativistic motion of dark matter. It means also that you can consider that dark matter doesn't move very much, and the velocity in reality is the velocity of Earth going around the center of the galaxy. And then here and this is the rate. So you can see that we have astrophysics input and we have particle physics input. So here there is the theory, here is our hypothesis, and this is the input for astrophysics. I will go quite quickly. So if I assume now that my nucleus in which I have the interaction and my dark matter have the same mass, you can calculate a little bit some numbers. So this is the local density for dark matter local in the halo. And so you can see how much it is. And so it's about, we have 1 WIMP per coffee cup, just to give you an idea. Obviously, we are on Earth with density of matter is much larger than the average density in our galaxy. But if we integrate to all the halo of dark matter in the galaxy, we'll see we have a lot of dark matter particle. The velocity is given by the velocity of Earth around the sun and then around the center of the galaxy. And so you can do a little bit of calculation to see more or less the kind of cross-section we are dealing. Just coming back to the velocity as a Maxwellian velocity distribution, that is the velocity of Earth around, let's say, in the center of the galaxy, but dark matter is not still, but it moves. They are speaking about in a non-relativistic situation, and this is the distribution that we are using. Some typical number, if I assume that my dark matter is 100 GeV, so is what we call at the electroweak scale, and I calculate the xenon target that has more or less an atomic mass of 100, so it's more or less of 100 GeV, mass and the kinetic factor that reduces mass is 1, and the velocity that we discussed before, we are seeing that my mean recoil energy, so when I have an interaction between dark matter and my nucleus, is about at the keV level. This is 30 keV, but what you need to keep in mind, we are speaking at the keV level. So the energy at which we need to build our detector, we need to build a detector that can see interaction in the keV range. So that is much below. I'm coming from collider to anything that you do in a collider experiment. The other issue that you are dealing is, how does the signal look like? Here is a log rate of my rate with respect to the recoil energy. And if I take the log, because here you have an exponential of this is the nuclear recoil energy, this is most probable energy of my particle, and this is the event rate per unit of mass that we saw before. And if I look at my signal, well, my signal is nothing more than a decaying exponential. And then when we are going to look at the background, my background looks really like a decay exponential. So my signal is not only very small, but it looks exactly like the background. So the fact that the rate of my signal and the shape of my signal really drive, and the energy of my signal really drive, how do we design this experiment? The other thing is important, all the calculation here that I'd showed before, so my numerology, was done assuming that the dark matter particle has the same mass of the nucleus, and I use 100 GeV for my particle and 100 GeV for my nucleus, so I use xenon. In reality, I can look if I look at my rate, that this is more or less, and normally you will see that we do the rate in events per kilogram per years or day. So you will see me all the time. I say these events is blah events per kilogram per day or per year. Depends on what? The density we discussed, the velocity, the cross-section, but also the mass of the nucleus. So if I put 1 here, is the rate we get. But in reality, your dark matter particle can be anywhere, if I'm a WIMP, from a GeV or sub-GeV, half a GeV, to TeV range. And so what happened here with respect to the material of what we call the material, my target, I'm building my experiment. So here we're looking at the maximum recoil energy that I can measure with respect to the mass of my dark matter. And you can see here that I have different elements from helium, carbon, silicon, germanium, xenon. And you can see that my maximum recoil energy that I can measure with respect to the mass changes with respect to my element. And you can see that lower mass will be seen if I have a low an element with a small nucleus, with a small number of proton and neutron, and nucleus with small mass. And as my element, like, for example, the xenon over here, is getting quite large, the xenon, as I say, is 100 GeV mass. Speaking as a particle physicist, everything, all the mass is in GeV. Over here, you see that the maximum recoil energy that I see, it starts, and the minimum is over here, is 10 to the on the mass, and you can see that larger mass will be seen, but smaller mass, so mass that are below the GeV, the xenon have a sharp cutoff at about 5, and GeV below will not be seen. So my detector will be non-sensitive. So it means that I don't have a single way of seeing my dark matter. So I need to use different targets because I don't know the mass of the dark matter. So if I have my hypothesis that my dark matter is on the GeV, 100 GeV bulk, I will go with detector with target xenon. If I think that my dark matter is a couple of GeV or less, I will go with targets that are helium that have a mass of about few GeV. And so this gives also the large complexity of the experiment we are going to see. My garden variety. Obviously, we have a dark matter interacting with the nucleus. So yes, there is a nuclear interaction, but there is also, and this is the complexity, I don't want to dwell too much, that there is also nuclear physics that comes into the game, and so not all the nuclear recoil energy, so not the rate of the events, changes with the structure of the nucleus that you need to take into account. So also not all the target, as you can see here, for example, with tungsten, is a target that could be used because at a certain point you will have that the target will not be able to see the dark matter because of the way of the shell model of the nucleus of this particular element. I spoke, and this is just touching, that I assume that the dark matter is a scalar, so it's no spin. So the cross-section depends on how many proton or neutron I have in my nucleus. But nobody tells us that the particle may not have a spin. In this case, I will be much more dependent on how many proton and neutron I have in my nucleus, and this will give us experiment that may be very strong exclusion or discovery potential when my particle is a scalar, but maybe reduced potential because of the shell model of the nucleus. So this is another thing to keep in mind. But from now on, we forget the spin dependent, and I will work on it in a spin independent way. Otherwise, they will be much larger. So what we say, well, we're speaking about the signal versus background. As I say, dark matter interacting with my nucleus and go away. This is what we can assume more or less is given by the latest result with the xenon experiment. We have less than 1 event per 10 kilogram a day, or 0.1 event per kilogram a day, or what we call a DRU. And you can see in this particular example, we have an 100 GeV particle with a nucleus of xenon and about 10 to 20 keV recoil of my nucleus. But then I have the background coming from, I don't know, it's not me, it's done. Neutron, that we are speaking about millions of events per day that have exactly similar kind of kinematics on their recoil. Because they are neutron and they don't have any other way to be seen, they represent quite a bit of background for our dark matter experiment. Electron and gamma in some target do too, and we will see later. So this is a little bit of the landscape, sorry. Need to put my glasses. We are dealing, and I leave you, this is more for an exercise later, to calculate how many dark matter particles interact with our target and how many atoms, radioactive atoms of potassium-40 we have in a banana, and understand the challenge of our experiment. So we say that we are looking at wind scattering less than event per kilogram per day, 0.1 event per kilogram per day. And we have swamp of background of events from nucleus, from neutron, and also other particles, because shear events between 1 million and 10 million, 1 billion. So how can I build an experiment in which the signal has no feature, looks like the background exactly? And my background is 7 orders of magnitude larger. I need to go in a place where my background is heavily reduced. So where the neutron that I don't want comes from? Well, the neutron comes from 2 places. One is from a cosmic ray. We are bombarded by cosmic ray continuously. And if I'm on the surface of Earth, I will have plenty of cosmic ray reaching us, million and million. And so I need to remove this contamination from cosmic ray, that is the majority. And the other comes from the fact that any kind of element, no matter how we think is non-radioactive, has a certain amount of radioactivity. And I will encourage you to calculate the rate of 100 GeV dark matter particle with respect to the activity of a potassium-40 in a banana. And you will see what we are dealing with. So how do I remove the cosmic ray? Well, if you look at the cosmic ray when they reach Earth, most of them get absorbed by Earth. And so if I go deep enough, you see that here muon, hadrons like pion and normally, muon and neutron producing cosmic ray as the depth as we go into Earth, as soon as they arrive, they get absorbed. The depth here in Earth is given in water, a meter for water equivalent, because we can have different density of rocks, so we transform everything in terms of density of water. And you can see that pion, neutron, and so on, normally they get heavily absorbed, and depending on the energy, maybe we can say that only very few of our muon reach deep underground. For this reason, all the underground experiment, all the dark matter experiment I will discuss, they are put in deep underground laboratory that are all over the world. These one, some are in the States, Japan, Italy, Australia. This again the stake. There is, this one is in Canada, and Jinping is missing. There is also one in China. And you can see that if you look, is related in muon flux, they are deep enough where most of the cosmic rays stopped, and they only have a very small amount of very high energy muon reaching us. The other bit that we need to deal, and I will go next lecture about the adventure of how we reduce the contamination of radioactive isotope in our material, will be done in the next lecture. So every kind of material, very few of our nucleus have isotope that, are not radioactive. The majority have radioactive isotope, and they are everywhere on Earth and everywhere in every element. And the spontaneous radioactivity like thorium, uranium, potassium, argon, and krypton and others, they are there and they emit neutron and other particles that they can contaminate and disturb our experiment. And when we go to the cross-section that we are speaking again of 0.1 events per day per kilogram per day, this radioactivity that normally we live with and don't disturb us is becoming quite a problem. And so when we build our experiment, not only we put deep underground, but we embedded our experiment in what we call the shielding. And in some experiment, we have also a veto to be sure that any of the radioactivity of the surrounding material penetrate our experiment. And then there is a big saga in how we select the elements that we do our experiment, our shielding of the experiment, to be sure that radioactivity is almost zero. So which kind of detector? As I said, depending on the target is important because depends on the size of the dark matter. The target with large mass, with nucleus with large mass, are better for large mass of dark matter. Lighter target better for lighter dark matter particles. And then depending on the target and depending on the mass of the particle, you can have different method of seeing. So we can have ionization charge, scintillation, or phonons, or measure heat. And so I will describe these three ways that they mainly. I will go to the major experiment, the large experiment that like xenon that are made of liquid xenon. I will discuss by the end scintillation light, in particular sodium iodide, and then I will start discussing on bolometer. That is maybe the new revolution in which they allow to see more and more small dark matter particle, and they are a big R&D going on. So what do we do when we build an experiment? I say we didn't detect the target and all of that. Normally what you will see, and I will show many times, you will have a plot in which you have the cross section, so dark matter interacting with baryonic matter and the mass of the particle. You will see that most of the time you will have a curve like that. That means that anything about this curve is excluded. And then in some case you have a small contour, means that inside this contour there is a signal. Now, if I wanted the micro section, as I do my experiment, if I want to measure or exclude cross-section, interaction cross-section that are smaller and smaller, what I need to do is increase exposure. So having an experiment that collect dark matter for many years, or building a very large experiment, multi-ton experiment. If on the contrary, I want to go on this side, that I want to measure WIMP with lower and lower mass, the lower threshold, well, this depends on the target. I need to choose a low target, but also a method to see the interaction that is not the same I'm using here, and here is where, as I say, bolometer are start coming in. When we do the sensitivity of an experiment of dark matter, we assuming that we will have zero signal and that the background look exactly like it is. Differently from the LHC experiment, another experiment, a collider, when we build an experiment of this kind, and then there will be also the neutrino experiment, we set what is the limit we think we can assume with our target mass, and we build to the experiment, screening every single element of the experiment to reduce radioactivity. So that is our goal. So it's not because we take more data that we reach here. We reach here is the same, is the requirement of the experiment. And then we work to get this requirement done. And so in the last 30 years, I would say, we had incredibly big expansion of the system. Now we are running what we call generation 2, and the next will be generation 3. There is also a generation 2.5, I would say, which we have larger and larger experiment, and we start working very closely with chemical engineer and so on for reducing the radioactivity into the material and a purer and purer material. So where we are today, so as I say, here in this part is again spin-independent cross-section and dark matter mass. This is correct. This is this current excluded, and this is as 2013. And this is where the actual experiment will reach eventually. Will reach eventually over here, this one there. There are a lot of planning experiments we will discuss, and at the end, they will reach over here. New technology that will go to mass, and we hope here, and then we will reach a point where dark matter detector will be so sensitive that our background is not the classical background of radioactivity, will be neutrino, and then the technology may even change because neutrino really look too much like dark matter to be distinguished. So as I say, we are in generation 2 and 3 at the moment. The generation 2 are the liquid normal gases that work now with expansion that will try to push. So liquid noble gas like xenon and xenon are pushing in this area, so going a lower cross section at higher mass. And then there is all the cryogenics experiment. There will be a talk, I think, from someone tomorrow and the day after about technology like bolometer technology that are trying to push a lower mass so that WIMP will meet axion and will cover the full space. Let me describe the big xenon experiment. These are the one that is providing the stronger limit like now. There are 3 of them running. Xenon, 1 ton in Italy, Panda X in China, and LZ in the USA. And you can see they have a mass. This is a TPC, time projection chamber over here. And inside these, there are various tons of liquid xenon. The largest one is LZ that has 7 tons of liquid xenon. And all of them are running. They have a huge amount of photomultiplier. And all of them are what we call dual phase TPC. So this is the liquid xenon detector. Let me see how they work. So it's a TPC, so there is here liquid xenon, and here there are photomultiplier that can see light. And what happened is that the incoming particle, dark matter particle, interact with the xenon, and release some light that gets collected by the photomultiplier, but it's also produced electron that drift, and also this signal that is called S2 will drift to the cathode, towards the anode, sorry, and will be collected. So when you have an interaction of dark matter or with your xenon, you will have two signals, one very fast, that is the scintillation, because it goes at the speed of light, and now another one that we call S2 after a period of time, because it needs that the electron drift towards the anodes and then produce light and then is recorded. So you can see here this time, the S1 is the time of which we have the signal arriving the light, and S2 after a certain time. As you can see here, the difference between these two signals, this is the drift time of the electron, and this one is typical or dark matter. Dark matter has a typical drift time of 20 microseconds. For example, a photon or an electron will be a larger drift time, and so this kind of experiment, like all the xenon experiment with the dual TPC, dual phase TPC, are able to distinguish neutron, the distinguish particle electron from nuclear, from neutron and dark matter, and so they have a very powerful background rejection. So they produce the biggest limit. So the latest one is LZ that just produced there. So we can see a cross section of 10 to the minus 47 is the best we ever seen. And you can see here again, as soon as we reach 10 GeV, the xenon experiments start losing sensitivity because the xenon is too heavy. But the fact that they have this dual TPC and they can distinguish a nuclear recoil produced by dark matter and neutron versus electron and photon give a very powerful detector. Neutron will be distinguished by dark matter by calculating all the neutron budget in your material to see how much neutron, the radioactive decay in your material will produce neutrons, so to again, to go very high purity material. Next generation will be a mega super detector. So the idea is that we need to reach the limits of this technology. So we will plan, the next generation is called LZD, and that will, xenon, LZ, and this new R&D called Darwin will be put all together. And we are planning a detector that could be between 30 to 100 tons of xenon, depends how much we can source xenon. And this is another drama and another adventure, because xenon is extracted from air. It's not mine, etc. You need a plant that takes xenon from air. The world produces about 30 tons of xenon a year. Most of that is used by medicine, so obviously you understand that graph. The other noble gas experiment that are coming to the fore, and they are quite powerful, are argon. Argon is quite light, so it's very good for low mass. We have DEEP in Snow Lab in Canada and Darkside in Italy. Here they don't use a dual phase TPC, they use pulse shape discrimination, so the difference of the shape that they read out when the particle reach the sensitive volume, and they can distinguish what they expected, the background and their signal over there. They are still not as big, as powerful as the xenon experiment, but they are coming to the fore. And you can see here, dark side over here. Obviously, you see they are not as performant as the xenon, but they produce, the hope is the dark side, and because it's lower mass, they can start pushing in this direction. Next will be dark size 50 tons in LNGS, and then Argo 400 tons of xenon. And how you produce it, of argon, how to produce high purity argon, you need a shaft 200-meter deep and start doing the distillation column. So this is another part. So the xenon and the argon are really, in particular the xenon, are wiping out everything above, say, 10, 15 GeV. And in the next few years, also with Darwin coming, and then also the argon, etc., they will really cover the full phase space until they reach the neutrino floor, what we call when neutrino is a problem. And they are mature, a sort of technology, and we are like in the area, really at the peak of their sensitivity. However, dark matter can be very small. Nobody tell us that must be at the electroweak scale, can be much part. And you can see again, I'm using the xenon target as we discussed, that the nuclear recoil spectrum for different WIMP mass, and you see that as the mass of the WIMP gets lower and smaller, the recoil energy of the nucleus became so small that your detector doesn't see anymore. There is not enough energy for producing ionization in your dual TPC, so you miss the detector. So you need to find something that sees this particle. And normally what you do, you go with different targets, for example, sodium iodide, gallium arsenide, germanium, silicon, that are all atoms with smaller with smaller mass. And so they can have a nuclear recoil, energy recoil that is large enough that we can detect. And so you can see here, for example, the low threshold is what is the expected cross-section versus mass for this xenon, but you can see for this lighter target there. And this is where all the R&D and the new experiment or the experiment that look at this area are going. But before we go there, as soon as we start going at low mass, even if I have a low target, is happening that when I look at the recoil energy that is released in my atom, the energy that is released in my recoil, in my kinematics, get released in my material less and less as excitation, electron, and so on. What we most probably, if you look, calorimetry and so on, but it's becoming more and more kinetic motion. So it gets the kinetic energy of the nucleus get transformed in heat. So as I want to go and measure or see dark matter that have lower mass, in particular at the sub-GeV, GeV and sub-GeV level, not only I need something light, but I also need a different technology because there is not enough produce of ionization or scintillation to be seen in a classical detector that you've seen up to now. So I need to see a detector that sees what we call phonon, that measure heats. And so obviously you can see, and phonon can be producing crystals, scintillation, semiconductors, superfluids. What is typical, so there is a variety of elements that we are going to see. That what is common to these elements, that if you want to measure very small quantity of heat, you need to put your target at a very cold temperature. And here we are not speaking about Kelvin, we are speaking about millikelvin. So what we call all of that are cryogenic state, but cryogenics, very push cryogenics. So we look, first of all, to a bolometer. So what we are doing, very cryogenic solid state detector. In a very cryogenic solid state detector, we are speaking detector that are put in what we call a dilution fridge. A dilution fridge is something that can cool matter up to less than 50 millikelvin. Some of these experiments could be also the aim to go 50 millikelvin, like water that you get at 50 millikelvin. And what's happening that when dark matter interacts with our element, with our absorber, the tiny element of heat that is produced in this kinetic, and the kinetic energy get transformed in heat, get collected with a detector that can see the heat. And if I look at the standard kind of detector, so if I look at the heat capacity of my elements when I have an interaction, I have that the change in energy with respect to the change in temperature of my element, because I had a kinetic energy released by my dark matter particle in my target, goes like the temperature to the third. How do I read this temperature? classically is that either transition edge sensor or NDT. We have, this is in the domain of quantum sensor, and normally are superconductive, for example, like the TES or other part. The interesting part that even if there is a very tiny production of scintillation or electron, there are some effects that can be exploited. So experiments that have bolometer normally not only can measure the temperature, but they can also measure some of the scintillation or the parts. So what we have is like here, this is a device that is a germanium detector, that show the difference here where they expect the signal, and this is where they expect, for example, the background due to electron, and here neutron. So between looking at the ionization versus the recoil energy, using this system, they have a very large, excellent discrimination. Sorry, the device is, no, this is a there's a double beta decay, so it's a molybdenum crystal. Excellent energy resolution, they are able to distinguish signal to background. So normally you don't need tons. All these experiments we are speaking now, you're going to see that from ton we go to kilogram and even in sometimes few grams. The largest of these experiments of this bolometer, cryogenics bolometer, is the Super CDMS at NOS lab. They have the incredible ambition to have a half a ton target. And this is the unit of detector. This is germanium. And this nice drawing over here is this, the TES to read the phonon. And they will be stuck in this detector in a column like this. And each column will be frozen at cryogenics temperature, a few millikelvin. And this will be the largest possible part. We are speaking about germanium. There will be also silicon, about almost half a ton, and will be the most sensitive experiment in the low mass for a long time. And CDMS is already producing data, so the Super CDMS will be ready not far soon. In addition, Super CDMS to the classical things that they see the phonon and they see some scintillation, when the particle interact, not only we have the prompt phonon that you can hear and you read, but there is also Luke phonons that get produced, and this secondary phonon improve the sensitivity of our experiment. And in Super CDMS, they use this effect, you can see here, to reach even lower energy recoil than what you could do simply looking at phonon. So as I say, Super CDMS will be the experiment in the future. There is another experiment, as I say, CREST. CREST is the experiment that dominates low mass, dominates the region below 1 GeV or dark matter, between 1 GeV and few MeV. And again, is a bolometer. The target this time is a complex target, is a calcium tungsten oxygen target, a calcium tungstenite oxide. And the tungsten doesn't do very much because it's quite heavy, but the calcium and the oxygen are light enough to see light dark matter. This is one of the modules you can see here. They have this aluminum oxide that is able to act as a light absorber. And then they have the thermometer that is a test, the TES, that measure the temperature. So here you have the temperature. Here you have a light absorber that also, the light that is absorbed is also read as a temperature, but this is produce a two readout of light and temperature. And they aim at 10 kilograms of mass, but they start working with very few parts. So this is how CREST look like. And these things over here, they look like a dishes, a pile is a dilution fridge. So you put things on this plate and you put things at millikelvin. So this is how the running experiment. They put strong limit in the sub-GeV case. Strong limits, when we speak about strong limit in the sub-GeV case, we are speaking about limits that are order of magnitude smaller, larger, or smaller in the sense than what we obtain with the xenon. So I would say that this kind of experiment, a cross-section of 10 to the minus 40, is many, many order of magnitude larger than what has been excluded by the xenon. And so in this area, there will be a lot to be done to get better limit. And the problem in this area is scalability. And the largest experiment at the moment, the measure that was able to go to millikelvin to cool down almost a ton of stuff at 15 millikelvin is Cuore. So the next generation will really benefit of R&D, not on the detector, but how on the dilution fridge. Now we are going silicon. As I said, silicon has been used quite a lot in energy physics, but not in this part. And so people start looking what we can do with silicon. Again, always in the part, silicon can interact. We are looking something that you saw a lot in the pixel. There is a particle interaction and there is an electron and a hole. And then if you have a very pixelated detector, you can see electron, alpha and muon. There is you can distinguish the various kind of particle. And you can also, because silicon is very light, see very dark matter particle. At the moment, there is an experiment called Sensei. It's only 2 grams. It's running at minus, very shallow, because it doesn't need to screen very much. And they're constructing in 100 grams of snow lab. And you can see that from here to scale will be large. And so here where we are now. And here you can see CDM light, and super CDMS will cover there. CREST is here, and CREST does very well here. And then, and you can see xenon disappear there with LUX. So future mass limit, well, low mass will be cryogenics bolometer, ionization detector like Sensei, and most probably using a different effect on the big experiment like the argon xenon, the Migdal effect, but I'm not going to go into it. Then there is the frontier at less than 100 MeV, again, bolometer, again, or superfluids, again, cryogenics. And here we are really going very far from classical particle physics experiment or classical physics sensor. And we are doing in the area of phonon, what we call acoustic phonon and so on. Before I finish, we are speaking about the other case, scintillation, sodium iodide case. Sodium iodide, you have an interaction, is a scintillation. There is something like, there is a scintillation when there is an interaction in the crystal. There is the electron get excited, and then as it get de-excited, the elements, there is emission of a photon with a wavelength that is almost in the ultraviolet visible. And so if I have the right detector, if there is an interaction of dark matter rather with my sodium iodide, it happens. This is a classical, I would say, very mature technology. And the way you read out the light is through a photomultiplier, in which we have a photon energy that is converted in electron and then is amplified. Sodium iodide, with respect to all the other, you can see that between experiment they run in experiment planning on sodium iodide, there is quite a bit. There's quite a large amount. The reason is that up to now, I show you only limits. But there is one experiment, this 20 years, more than 20 years, you see a signal. And differently from the other experiment, instead of seeing some signal above the background, they're looking at a modulation flux due to the fact that when Earth goes around the center of the galaxy, the velocity of Earth is modulated by the rotation of Earth around the sun. And so I have that the velocity changes during the year with a period that there is a December and June, there is a maximum and a minimum. So in June, the velocity is maximum, and in December is minimum. So the flux of dark matter particles that I see on Earth changed with the same modulation. And so if I look at the ratio now, there is the calculation that we did before, plus another term that is this modulating terms for the change of velocity that comes from these modulating terms of the velocity that goes like the cosine. And so if you look for this signal, you will have a signal that is modulating over the here. And if you see this flux of dark matter that change over the here, is a very model independent signal. You nail dark matter. And before I finish, so there is this experiment, sodium iodide, that has been running for over 20 years that you can see exactly the modulation. This is gamma first, second, and third. And it's been seen this signal for many, many years. There is, I would say, 13 sigma confidence level, the same expected phase, very similar what we expected, and amplitude. The issue for this experiment that if we assume the WIMP hypothesis that we did before, the vanilla one, this signal should be excluded by all the other experiments. However, it's 30 years that this experiment, no matter what you ask, can you see that, can you see that, can be possible that, see this modulation, and this is the gamma enigma. People may believe or not believe, there's been a lot of controversy, but the only way we have to eliminate this experiment, say yes or no, is to repeat the experiment. And that's why there is all this activity all over the world. Now, when you have a signal, and I just do there and I will finish in the next lecture, there is a problem that comes in all this story, is that when you have a signal, now you need to see what you are seeing. Because when you don't see anything, you can have all your hypotheses, you see nothing. You may be aggressive or not in your limit, but you see nothing. But what you are seeing, something, what you are going to see. And the fact that when I have an interaction with my sodium or iodine, I don't know what, I need to transform the recoil energy in the signal, what I'm seeing, into the electron equivalent energy that I'm reading with my photomultiplier. And this one is this quenching factor here, this conversion factor that depends a lot on the nuclear physics. And there have been a lot of measurement of this quenching factor over here, and all of them, none of them is close to each other. And depending on which quenching factor I assume, I may see or not see the signal. So before I leave, I'm leaving with the two running experiments, and we will see future experiment later. And when we look at the two running experiments, cosine and Anais, Spain and Korea, they try to cross-check gamma. We are speaking about sodium iodide crystal. Gamma is 250 kilos of target. They have also in the 100 kilos of target. I would say cosine has a lot of target, most of it useless, to be honest, because they're very high background. They realize later that the crystal's been exposed to too much cosmic ray. And now here we are looking at what is the signal. Well, this is what you see, that is your rate, what you measure with respect to the recoil energy. And where is your signal in this curve that is the recoil energy with respect to the rate? Well, depends on your quenching factor. So if you use the quenching factor that normally gamma uses, your signals sit here. If you use another quenching factor that is the further one from gamma, you see your signal over here. So your region of interest where you see the signal change from your quenching factor. And this is reflected from the experiment. So this experiment here, this is gamma, this is cosine, and this is Anais, as presented by the experiment. And so you can see that gamma see a signal, cosine is in the middle, and Anais excludes. But then when I change, for example, here for sodium iodide, these two other quenching factors, you see that the central value of this experiment changes and they became closer and closer. So quite an interesting one. So before, and I will go in the next, I'll leave you say that, do we exclude or not exclude gamma? Well, we still don't know, and that's why we have so many experiments, and then what we need to do to exclude or not this signal. Thanks.
Thank you. Okay. Now floor is open for question.
Thank you for the nice presentation, ma'am. Hello. So my question is, the only thing we surely know about dark matter is that it interacts gravitationally.
Yes.
And apart from the fact that we are missing some mass, are we also looking for some astrophysical observable for the detection of dark matter?
Yes, so there are some of my colleagues in the center that are looking at this black hole that could explain, but the way you look is looking at micro lenses. So you see if, when light bends, there is some particular part of our galaxy that instead of looking at the diffuse, because the halo is a diffuse, like you have some, something that they look like very large objects, so you have a bigger bending. At the moment, they're almost more and more excluded. The other explanation is that we need to change gravity. Again, it's very difficult to, the difficulty of that modified gravity is that they can, if they have two parts, you need to explain the large structure, the large scale structure, the small, in our solar system, and they still unable to reconcile the two. So that's why people are still looking there. And then there is someone there.
In slide 25, you had this term xenon neutrino
Yes.
fog. What is that?
Sorry, xenon?
In slide 25.
The dual phase?
No, it was showing the limit plots in the experiments. Yeah, not this. Slide 25.
25, thanks. Okay, here.
Yeah, that xenon neutrino fog.
Yes, the neutrino fog, okay. So you can see here, as the cross-section is decreasing, so the interaction became smaller and smaller, we need experiments that are more and more sensitive. And when we reach this cross-section, our main background is not anymore radioactivity, because we assume that we can control radioactivity, otherwise we will be unable. But then there will be neutrino, because we will be in the same range of cross-section of interacting with neutrino with matter. And so we are doing that our background will not be neutron, but will be neutrino. And that is very complicated, because the neutrino looks exactly like dark matter, and I'll let him to explain, we'll see. And then we need to change technology. So we need to go directionality. Dark matter, because it's diffuse in the galaxy, is, if you look at the direction where dark matter comes, will come from the direction Earth is moving towards, so the Cygnus constellation, while neutrino will be coming mainly from the sun, or will be a neutrino fog that will be like, we are in a fog that is not really a direction.
Okay. Thanks for the excellent talks, and hopefully tomorrow we will have a much better idea and better talk. And now we'll have a 5